All right, let's take a look at an example of a type of collision, if you will, that we're going to call a separation. And so this is actually the opposite of a collision, if you will. When two objects that are stuck together, something happens in between them. Some may be explosion or some sort of force is applied to both of them to send them flying apart from each other. So you could imagine this like if you're sitting in a rolly chair in your bedroom and you throw a textbook onto your bed. Essentially, that is a type of separation. Two objects who were initially one object together are now going in separate directions, or they're being separated. So this actually holds the same idea as before. The momentum before and after the separation will be the same. So if we have two carts initially at rest on a frictionless track and some explosion happens in between them, so some explosion happens here to cause them to separate, and we're told that the blue car has a final velocity of 4 meters per second to the left and the red car has a velocity of 8 meters per second to the right. If the mass of the red car is 5 kilograms, let's find the mass of the blue car in kilograms. I'm going to solve this problem using the momentum table like I have before, but in this case, I already have a diagram, so I'm not going to draw one. I know that the momentum of the red car and the blue car before the collision is 0. Why is that? Well, it doesn't matter how much mass they have. They're both motionless. Their initial velocity is both 0, so therefore they have no momentum. So after the collision, I know that the system's momentum must still equal 0, right? These have to be the same in order for momentum to be conserved because my change will always be 0. So what that means is the momentum of the blue car, in this case, and the momentum of the red car together will add up to 0. In this case, the momentum of the red car is something I can quantify right now. I know the final velocity was 8 to the right. That's going to be positive. So positive 8 times 5 is going to be 40. This is kilogram, and this is in meter per second this time. And therefore, I don't know the momentum of the blue car, right? But I know that it's going to be the mass of the blue car times the final velocity of the blue car. So I can look at this after collision column and see that 40, I'll write this in a different color here. So 40 plus the momentum of the blue car after the collision has got to equal 0. So in other words, the mass of the blue car times the velocity of the blue car after the collision is going to be equal to, almost missed the negative sign there, negative 40, right? So that means that the mass of the blue car is going to be negative 40 divided by, I was given the velocity of the blue car. That was 4 meters per second to the left. In other words, negative 4 meters per second. And again, if I show my units here, you'll see that the meters per seconds will cancel, and I will just get 10 kilograms. All right, there we have it. We've solved for the mass of the blue car. You could have also, once again, seen this as the red car gained 40. That was positive 40. And that means that the blue car had to lose 40. And so if it started at 0, essentially, then 0 minus 40 would be equal to the momentum afterwards, or in other words, the momentum after would be equal to negative 40. Okay, so again, two different ways of solving this problem, but using the table makes it a huge help. All right, let's take a look at one more example of a separation.